Right, so we'll continue from where we stopped in the last class, which is experimental chemistry, practical skills. I explained about the safety symbols and the common laboratory apparatus. I told to highlight these apparatus. This is important: the still head and the receiver adapter, and then different methods of collecting gases, which is based on the density of the gas and solubility of the gas. We discussed that, and methods of drying a gas was discussed, and also in detail we discussed about the melting point determinations. I think I told the rest of the fractional distillation and refluxing I've explaining today, and also filtration under filtration under gravity was explained. As for the test for the cations, let's see how to test these cations. There are tests for cations, anions, and gases to be studied. When it comes to cations, the positive ions, you have ammonium, copper, ferrous, ferric, calcium, magnesium, aluminium, and zinc. Now, all the cations can be tested by adding a limited sodium hydroxide, excess sodium hydroxide, limited ammonia solution, and excess ammonia solution. Now, when you add limited, you write the observation, and then you further add excess and then see what happens, whether your precipitate dissolves or not. The purpose of adding excess alkali, now you have two types of alkali here. This is sodium hydroxide is strong alkali, whereas ammonia solution is ammonia in water, which is in fact ammonium hydroxide, which is a weak alkali. So in testing for the cations, you add strong alkali, few drops, check if there are any precipitate, right? If there is no precipitate, then you write no precipitate. If there is a precipitate, then you add excess sodium hydroxide with the same precipitate and see if the precipitate dissolves or not. The purpose of adding excess is to check whether the precipitate further dissolves or not. Certain hydroxyl precipitates of the D block dissolves in the presence of excess alkali. Same thing you do with ammonia. So why, you might wonder why you are testing with both strong alkali and weak alkali. That's to distinguish between various cations. Now if you notice, some cations have the same observation. Like for example, to take aluminium and zinc. Aluminium and zinc, you get the same observation with NaOH. You get a colorless solution, white precipitate resulting in a colorless solution when you add excess. Same observation for zinc. So how do you know whether it's calcium or zinc? By just this observation. Now when you add ammonia, which is a weak alkali, you can easily distinguish aluminium from zinc. And you notice that the observation in the presence of ammonia, when you add ammonia, the zinc dissolves in excess ammonia but not aluminium. So that's the importance of testing with strong alkali and weak alkali separately, because otherwise you get almost similar observation. Now see, magnesium and aluminium gives the same observation with aqueous ammonia, which is ammonium hydroxide, but the observation differs with sodium hydroxide, right? So this is the importance of testing cations with strong alkali and weak alkali, right? We'll be studying in A2 why certain hydroxyl precipitates dissolve in strong alkali and in the presence of weak alkali. Now let's see the first test, which is ammonium, and also these are not group 1, group 2 elements, except for the magnesium here. It's a group 2, because most of the group 1 elements you cannot identify by precipitation test. To identify the group 1 cations, you have to carry out a flame test. But most of the D block elements can be identified by their characteristic colors in the presence of strong alkali as well as weak alkali. Right? So let's see first of all the test with ammonium ion. Test for the ammonium ion, you add a strong alkali, sodium hydroxide, and warm, you get ammonia gas. So reaction which takes place here is that ammonium ion reacts with the alkali and release ammonia gas, and this ammonia gas can be tested with moist red litmus, because ammonia is an alkali gas the moist red litmus turns blue, right? So we don't test ammonia with ammonia. We don't add ammonia solution as a test for ammonia, because ammonia solution is ammonium hydroxide, right? So it itself contains ammonium ion. So that's why we don't test ammonia with the ammonium chloride or ammonium hydroxide. Ammonia solution is ammonium hydroxide. The test for the copper 2 plus ions, when you add aqueous alkali, strong alkali with a blue precipitate, when you add excess strong alkali, it doesn't dissolve. But same observation for weak alkali, ammonium hydroxide, with a blue precipitate, but when you add excess, it dissolves to form a deep blue solution. So that's the difference between the sodium hydroxide and ammonia, but both gives initially the same observation, but when you add excess ammonia, the precipitate dissolves. The next is the test for ferrous. Is Fe2 plus is ferrous, Fe3 plus is ferric, right? That's the difference. Ferric, we add the suffix ic when the oxidation number is high. So this is ferrous and that is ferric, right? So you add NaOH limited, you get a dirty green or dark green precipitate, which is insoluble in excess alkali. Almost same observation is seen with aqueous ammonia as well. Same observation is seen with aqueous ammonia, dirty green precipitate, which is insoluble in excess ammonia. That's the test for the ferrous ions, which is Fe2 plus. The next is the ferric. You get red brown or rust brown precipitate, which is insoluble in excess alkali. Insoluble in excess alkali, that is ferric. Ferric is Fe3+. Rust brown precipitate, insoluble in excess alkali. Next is calcium. You get a white precipitate, which is insoluble in excess alkali, which is strong alkali. And for weak alkali, you will not see a precipitate for calcium in most cases. Sometimes you might slightly see a precipitate, that is not always, but generally for calcium, you will not see a precipitate in the presence of the weak alkali. One second till I get the video for the calcium. I think for some reason the calcium is missing. Anyway, so magnesium likewise, you get a white precipitate which is insoluble. That's the only white precipitate which is insoluble in both alkalis. Strong alkali and weak alkali, magnesium is a white precipitate which is insoluble. That's the only ion which gives the same observation the white precipitate insoluble for both strong and weak alkali. As for aluminium, you get a white precipitate with sodium hydroxide, and that white precipitate dissolves in excess sodium hydroxide, but the white precipitate does not dissolve for the ammonia, right? It's ammonia, because it's a weak alkali, aluminium cannot dissolve, ammonia cannot dissolve the aluminium hydroxide, the weak alkali, the precipitate. So that's how we test for the aluminium ion. So with sodium hydroxide, the white precipitate dissolves. With ammonia, the white precipitate does not dissolve. As for zinc, you get a white precipitate which is soluble in both strong and weak alkali. So that's opposite of the observation of magnesium, where the magnesium, the white precipitate does not dissolve in both, whereas zinc, that's the only ion where white precipitate dissolves in both. This is a summary of the test for the cations. As for test for anions, first of all, carbonates. Any carbonate, when you add an acid, it liberates carbon dioxide. Certain carbonates, when you heat, you get carbon dioxide, other than the group 1 carbonates. Of course, group 1 carbonates will not decompose except for lithium carbonate. Other than that, any other carbonate, when you heat, it releases carbon dioxide gas, which turns lime water liquid. That's how you test for the carbon dioxide. Lime water is calcium hydroxide, and when you send carbon dioxide, it forms calcium carbonate, which is the milky color. So these are tests for carbon. You can add any acid to a carbonate, or just simply warm to decompose. So lime water is calcium hydroxide, so it reacts with carbon dioxide to form calcium carbonate plus water. And further, if you send carbon dioxide to this calcium carbonate, you get calcium bicarbonate, which is calcium hydrogen carbonate or bicarbonate. So further, when you send carbon dioxide, the lime water, the milky color disappears. It turns colorless again. So it's very important when you send carbon dioxide through lime water to carefully observe, because if the rate of the carbon dioxide flow is very high, you might see the milky color only for a few seconds, then it will disappear and forms a colorless calcium bicarbonate. And especially if you are heating the solid, you have to also be careful of the suck back, because when you take the boiling tube away from the flame, there will be a vacuum created, and then what happens is the lime water gets sucked into the hot solid calcium carbonate. In that case, the boiling tube will crack because of a cold solution, calcium hydroxide being added to the hot solid. Right? So in that case, you have to be careful to avoid the suck. In order to avoid the suck back, you have to first remove the lime water from the delivery tube before you remove the flame away from the carbonate. And likewise, the bicarbonate, same test for the bicarbonates. You get carbon dioxide when you add acid or when you heat. As for the bicarbonates, any bicarbonate will release carbon dioxide, even though if it's a group 1 bicarbonate, because group 1 bicarbonates will decompose. That will give the carbonate carbon dioxide plus water. But other than that, any other carbonate, it will get further oxidized to the oxide. As for the halides, chloride, bromide, iodide, you acidify with nitric acid and followed by the silver nitrate. You get a white precipitate for silver chloride, a cream precipitate for bromide, which is silver bromide, and a yellow precipitate for iodide, which is silver iodide. Now, it's very important to acidify the solution with nitric acid, because this is done to prevent the formation of silver carbonate, because among the salts, most common impurity is a carbonate impurity. Many salts contain carbonate impurities. So by adding the nitric acid first for these tests, you're removing that carbonate. You're preventing the formation of silver carbonate. If there's carbonates, what happens? Silver will react with the carbonate to form silver carbonate. The silver carbonate is a white color solid, so you get deceived. Sometimes you will think the precipitate is now chloride, whereas it's a carbonate, because silver chloride is also white. So sometimes you will see the yellow color of silver iodide as cream color, because the white color mixed with the yellow color, right? That's the reason why we acidify with nitric acid, to remove the carbonate. But it's very important that you acidify before you add nitric acid.